So this is the homework, section 2-3, page 84. 1, 7, 11 through 29, odd. 33 through 39, odd. 45, 47, 55, explain number 55, and 57. And so what this is, it'll just ask you, it'll say, here's this thing. What is f of x? Or what is the limit of f of x as x goes to whatever? It's good. It's probably going to be difficult. It may be difficult, maybe not. If you're really paying attention today, you might catch the hint that I'm going to drop. You probably won't. Because I'm not going to be very forthcoming about it. But the thing is, what you should do is if you're just stumped, just look at the answer in the back of the book. From there, you'll go, oh, okay, and you should be able to reason out why that's the case. That's what I want. The answer in the back of the book is something like 8 or something. I don't know. It's just some number. But you should be able to look at it and reason and go, oh, okay, this is probably why. I don't really remember what you said, and I'm not going to go back through the video, but it's probably this. So that's what I'm looking for. Just like the answer is simply a number, but I want more than that. I want you to explain why that's the case. And I said 57. So, okay, we got a lot. And so, like I said before, this is going to be due next Thursday. So you have 1 full week to do this. Why am I being so generous? Well, first off, this is much long. Well, not much longer. Sometimes this is 20 questions. You'll probably many times this year have 20 question homeworks. Suck it up, you're in calculus. My reasoning though for giving you a week is that next Tuesday, next time we meet, we're going to discuss something, and I'm not going to assign any homework on it. And it's something that if you were taking this class at this level at a college, you probably wouldn't even talk about it. They might mention it, and you probably most often would not do what we're doing. I'm going to jump into the lecture, and then I'll explain what it's going to be. So because it'll lead in nicely. So without further ado, limit laws. So like I said before, we're not going to be plugging in a bunch of numbers to evaluate limits. Like that's not how we're going to do it. We're going to use limit laws, okay? And I will give you examples, and this will all become much more clear. But we're going to suppose that c is a constant, something like 5 or pi, right? Something that doesn't change as x changes. Suppose that c is a constant, and that the limit of f as x goes to a and the limit of g as x goes to a both exist. That is, they're finite numbers, right? So this is some number. This is also some number, right? That those limits exist. Then, these should be just so intuitive, right? That the limit of a sum is the sum of the limits. That's one way of saying it, right? Like, if you add 2 functions together and get a new function, and you take the limit of that function, it's the same thing as if you'd taken the limit of this one, taken the limit of that one, and then added them together, right?
So it distributes. The limit distributes.
Yeah, you can think about that. The limit distributes over addition. That's another way of saying that. The limit also distributes over subtraction, or the limit of a difference is the difference of the limits. The difference of the limits. There you go. And this works both ways, right? So if you're trying to evaluate this, and it's easier to evaluate this, you might want to go in this direction. So on and so forth. Okay, I'm just going to say these, that a constant times a function. Okay, that's what that means. So like for instance, here's a function, and a constant times it would be like that. Or if you saw this right there, right? You could say, well, hold up, I could factor this out. If this showed up in a limit of some sort, right? You could say, well, that's the same thing as pulling that out. And I could just pull that out, right? Pull it out and do the limit first. Do the limit of the thing and then multiply. That's what this is saying, right? Is that if you have a function, you're taking the limit of it, and there's a constant, you could pull that constant out, evaluate the limit, and then multiply by the constant. Another way of saying that is that constants factor out of a limit. There are other. How does the book say it? The book says The limit of a constant times a function is the constant times the limit of the function. So yeah, okay. Here's another one. The limit of a product is the product of the limits. Okay, two functions f times g, right? And that would be something like this. Like if you have x squared minus 1, and you wanted to take a limit of that, that's the same thing. Since x squared is the same, x squared minus 1 is the same thing as this right there, we're taking the limit of that, it's the same thing as you take the limit of the first, the limit of the second, and then multiply those two results together. It's the same thing. Or it also works in reverse. You might find it necessary, given something like this, to go back and do it this way, right? All of these things work in reverse. And here's the tricky one. The limit of a quotient is the quotient of the limits if the limit of the bottom one does not go to 0. If it does go to 0, we're going to talk about that. Okay? But you cannot, but what this is saying is like, you know, usually you could just break it up. Do the top, do the bottom, then divide them together. But if the bottom works out to be 0, then we have some work to do, as we're going to see. Okay? So here are some examples to kind of make this, it's somewhat abstract here. I'm going to say, suppose that the limit as x goes to 3 of some function f is equal to 3. Suppose that the limit as x goes to 3 of some other function, call it g, is equal to 4. And we're going to suppose that the limit as x goes to 3 of some other function, let's call it h, is equal to 0. Okay, then let's say we want to evaluate the limit as x goes to 3 of 4 times f of x minus 2 times g of x. Well, what these limit laws tell us is that, okay, the limit of a difference is a difference of the limits. And so this is the same. And I'm going to be really sloppy here and not write as x goes to 3 below this limit. I'm just going to be sloppy, okay? Now, that's a constant times f right here. And so that tells us that the constant pulls right out. And so I could go, okay, 4 times the limit of f minus, this is also a constant. I could pull this out, 2 times the limit of g. And we're given that the limit of f of x is 3. So this is the same thing as a 3 right there, minus 2 times. We're given that the limit of g as x goes to 3 is 4, so we can just plug in 4. And so this is just 12 minus 8, which is, what, 4? Okay, so there you go. Okay, that's what all these limit laws are telling us. It's going to be much easier to do a lot of stuff that we have to do with these laws. Now, why are these laws true? Normally, anytime I put something like this up here, we're going to prove each one of these. In order to prove each one of these, we need the rigorous definition of a limit. And that's the thing I was hinting at earlier that we're going to talk about Tuesday, but I'm not going to assign homework. In fact, I was talking to Mika this morning. Remember, Mika has a PhD in seismology, math heavy. She has a minor in mathematics. She never saw that definition of a limit, not once, right? So it's like, it's kind of in the weeds, but it's important because we really need these. We're going to need these laws for the rest of the course, but you can't prove them without that rigorous definition of a limit. So I want to go through. We're gonna do it. We're gonna prove like 1 or 2 of these after we get the rigorous definition. But it is so far in the weeds, and I never saw it actually. Like, I had a teacher write it up on the board, and that was it. But I never actually worked with it until I was a math major and I was taking analysis. And so when you take analysis, that's when you really have to work with the rigorous definition of a limit. So we're going to do that. But I'm not going to assign homework on it, and we're not, I mean, I might ask you what is the rigorous definition of a limit, and you write it up, but we're not going to work with it. I'm not going to assign homework on it. You won't be tested on it. Because nobody is, really. Like, you can, again, like, right at this point, we're counting on our fingers, right? We're adding by counting our fingers, and that's what you need to do before you could actually jump into what addition is, right? And so if you want, you can take that rigorous definition of a limit, go take analysis, and you'll work with it until you're sick of it. But right now, it's more important that you could apply this stuff and get a feel for how limits work. Does that make sense? Okay. Oh, there was one more I wanted to do, darn it. Okay, you notice I had this up here, the limit, and I'm not going to write as it goes where. F of x was 4, and I had the limit of h of x was 0. Well, then what is the limit as x goes to wherever it goes? I hope it doesn't bother you that I'm not writing that there. Okay, you'd say, well, this law tells me that I could do the limit of the top and the limit of the bottom, but the bottom's 0. This is a number, and that's 0. And so we would conclude, not necessarily that the limit doesn't exist. In this case, you can, because you know that that's 4. That limit doesn't exist. It blows up. But this right here, this would just tell us, well, we can't use the limit law. And if you didn't know this right here, if you didn't know that, if this were just a big question mark, you'd say, well, I don't know. It may or may not. We don't know. It may or may not actually do that. What would it have to be for it to be a question? Because like I said, if it were 4, you could say, in fact, if it were 4, you could conclude this limit does not exist. If it were a -7, you could conclude this does not exist. What would the numerator have to be for there to be a question in the first place?
0.
It would have to be 0. Because that's the only way you could say, well, as we've kind of seen before, right? If you have something like this, the limit as x goes to 1 turns out, right, like you could actually evaluate that because those guys happen to cancel out. But if you did the limits x plus 1, x minus 1 over the limit x minus 1, as x goes to 1, you would get 0 over 0. And then you'd say, oh, wait, hold up. Maybe there's more I could do here. And indeed, that would be cancel that kind of thing out. There's some other things we're going to see. But this is the idea, okay?
So if it's 0 over 0, there might be something you can cancel.
It may be or maybe not. We don't know. We have to do more
If
work.
it's like 5 over 0, there will never be something you could cancel.
Say again?
If it was like 5 over 0, there would never be something
Right,
to cancel.
right. And so in the original case where we knew that it was 4, you could say does not exist.
Okay.
And you probably, yes, you would be able to write that it goes to positive infinity, but that means the same thing as it does not exist, right?
Yeah.
Okay. Because just because it goes to positive infinity or negative infinity doesn't mean that it exists, right? Okay. Everybody got that?
Yes.
Okay. Cool. So moving on, and we're gonna go through this real quick, but then I got a bunch of examples, and it should clear up anything if I'm kind of being a bit cavalier here. So, okay, from these first 5, which you could prove with the rigorous definition, from these you could take these and say, what happens if f and g are the same? And you could plug in f here, and you'd find that, oh, the limit of 2 of these and so on and so forth, and what you could get are the following. Here's the 6th limit law. It's the limit, as x goes to a, of f of x raised to the nth power is equal to the limit as x goes to a of f of x, all raised to the nth power. And that is where n is a positive integer. Okay. We did this like 2 years ago with logs. Remember there was that interesting thing with logs where you could say, well, if log of a times a is the same thing as log a plus log a, then you could generalize this and say, well, log a to the n must be log a plus log a n times, right? And so, in other words, log a plus, and you do that n times, that's the same as n times log a. This is a similar kind of thing you could do using these right here to derive this, okay? But it's saying if you have some function, maybe it's x squared plus 1, and you raise it to the nth power, and you want to find the limit as x goes to something, let's say as it goes to 1, you could just say, well, I could just take the limit as x goes to 1 of x squared plus 1, which would happen to be 2, and then take whatever that is and then raise it to the nth power. And so if n were something like 7, this would become pretty easy. You could just say, well, I'll just do this. Take that limit, which happens to be, what is that limit? What would you think it might be as x goes to 1? 2, right? I mean, basically, there's no problems with this. You could just plug in the 1, you'd get a 2, raise that to the 7th, whatever that is. That's what that one's telling us. We'll do examples, don't worry. Moving on, I want to get all these up here. 7. The limit as x goes to a of a constant is just that constant. It seems kind of cheap, but x, there's no x. It's like, you know, if you have a constant function and you write f of x equals 5, you're like, there's no x there. But it's still a perfectly good function. This just means that for every value of x, if it's 0, it's 5. If it's 1, it's 5. Same kind of things happening here.
Numbers have limits, but they're just
themselves. Yeah. Well, we're treating c as a function, right? We're kind of saying this function, f of x, is just a constant function. And you can say, well, what's the limit as it goes anywhere?
Oh, I see.
Yeah, and it doesn't matter where a is. A could be here. Well, if it's constant, it hasn't changed, right? That's what this is saying here.
Yeah.
Everybody get that one?
Yeah.
Okay. Here we go. 8. The limit, this might come as a huge surprise to you. The limit as x goes to a of the function x is a. You have the function x. This is f of x equals x. You know that function very well. And as you go to a, it gets closer and closer to a. Yeah.
Okay.
Yeah. What this tells us, though, is that once we get it down to x, we could just plug in whatever that number was.
Yeah.
And we could also, and you see, I kind of already did that when I said, what's the limit as x goes to 1 of x squared plus 1? I kind of used these two facts. I said, well, you know, if you just plugged in a 1 there, you could do that, right? That's kind of what I'm saying here, plug in the 1. And then I was saying, well, this right here, you kind of do the inside thing first, right? You know, that's what again, we're going to do some examples. I'm going really fast and furious through all of this. 9, the limit as x goes to a of x to the n is a to the n. How did I get that? Well, I used these two together in conjunction, like I just said, right? Since it's the case that you could take a function raised to a power, this is a function raised to a power, and do the limit inside, and then raise it to the power. And since x going to a just gives you a, we use those two in conjunction to give us that, right there. In other words, just plug it in. Real simple, just plug it in, okay? But again, all of these laws, right, all of this comes from repeated use of these, and all of this comes from the rigorous definition. So all of this, I'm telling you something that you probably already sensed when you first started working with these. But by writing all this up, I'm kind of confirming here that yes, this is all based on a solid foundation here. So So the same way that powers work, where you just basically plug in the value with a power, you could plug in the value with a root. If you have an nth root of something, it also works.
Yeah.
Okay, that's all that's saying. And this is, though, n is a positive integer.
Oh, and A is.
And A is positive. Yeah, it does work if A is negative, I think. I'm pretty sure it still works if A is negative, but we're not going into complex numbers, right? And A is positive if n is even, right? That's the key. And you guys already, you remember, right? You've seen that at this point so many times that you're like, yeah, I know where that's going. Okay, x goes to A. The limit as x goes to A of the nth root of a function. So now maybe f of x is like 3x squared minus 5x plus 2. Well, that's the same thing as you evaluate the limit as x goes to A of that function, and then you take the nth root. That's, again, assuming f is positive at A.
Wait, so if the function is like a negative function? Wait, what is that?
So at A, right, so here's f, right? Here's f, it does this. At A, if it's positive, you're good to go. If A is over here, problems. If n is an even number. Again, that's the stuff, really don't care about that. In fact, I wasn't even going to write that stuff up there. Because this is the idea, is that can you do this stuff? And I'm telling you, yes, these are the laws. We can do all of these things. Okay? Okay. I'm going to get rid of all this stuff, because now it's taken up the whole everything. It's in your book, okay? So we can do all that. Those are the limit laws, and with those, we can actually start doing something interesting, finally. And so here is an example, number 4. We want to find the limit as x goes to 2 of 2x squared plus 1 over x squared plus 6x minus 4. Well, the limit laws tell us, but basically, like what we could just do right now is just plug in a 2. We could just plug in a 2. But let's just make sure that that's the case, because I want to one time and one time only use the limit laws so that we could, like I'm telling you, you could just plug in a 2. Let's prove that you could just plug in a 2, okay? And what I'm going to do here is say, okay, one limit law tells us that the limit of a quotient is a quotient of the limit. So I could do the limit as x goes to 2 of 2x squared plus 1 over the limit as x goes to 2 of x squared plus 6x minus 4. Okay, now again, limit laws, we have a sum in here. So I could say, okay, I'm going to break this up and say that's the same thing on the top. The limit of a sum is the sum of the limits. And I'm going to stop writing x goes to 2 under my limits because I'm lazy. Okay, I shouldn't, but I'm lazy and I'm going to do it. So here's the limit. 2x squared plus limit of 1.
Which is just 1.
Which is just 1, but we'll get there. We're going to apply these laws one at a time now. Here, okay, we could say, we could say that's the same thing as the limit of the x squared plus 6x minus the limit of the 4. But that's another sum, so we could break that guy up and say that's the limit x squared plus limit 6x minus limit 4. Okay, so I'll just write all that out. The limit of x squared plus the limit 6x minus the limit of 4. Everybody got that?
You can factor out the 6, right?
Yeah, and now, well, let's do this. Let's factor constants out. I see a constant there, and I see a constant there. So let's factor out constants, and that gives me 2 times the limit of x squared plus And why don't we go ahead and take care of just all the constants? That's a constant. The limit of 1. Here's your function. It's 1. What's the limit as x goes to 2?
1.
It's still 1, so we'll just write 1. Right, that's all that means. Same thing down here, only now it's a 4. So the limit as x goes to 2, still 4. So that's a minus 4 down here. You told me we could factor out the 6, and you're right. That's 6 times the limit of x. And this is limit x squared right there. Okay, so now, I hate how that happens. So now, okay, here's how I'm going to do the top with the squareds. I'm going to use the limit law to say the limit of something raised to a power is the same thing as taking the limit of the thing and raising it to that power. Everybody got that? Right? That works. Same thing down here. The limit of something to a power is the same thing as the limit of the thing raised to the power. Noting that the power is a positive integer. So that works with what we said. Okay, now finally, this is the limit as x goes to 2. Limit as x goes to 2. X goes to 2. The function x goes to 2 as x goes to 2. So we have 2 times 2 squared plus 1 over 2 squared plus 6 times 2 minus 4, which is 4, 8 plus 1, 4 plus 12,
16
minus 4. So that's 9 twelfths, which is
3
2/3. Wait, no.
That's 3/4.
3/4. Now, like I said at the beginning, you could have just plugged in a 2. Like, all right? But I want to show you why you could just plug in a 2. These are polynomials. Polynomials obey these laws. There's nothing crazy going on. You could just, like, basically polynomials are the things that do this, really. It just works with all polynomials. You could just plug it in. The only problem is when you do that, so this is how, if you gave me this problem, my first thing I would do, I'd say, well, I'm just going to plug in a 2. And I'd plug in a 2 in this case, and I would get 2 squared plus 1. 2 squared plus 6 times 2 minus 4. And I'd say, yep, that's 3/4. Okay, no problem. But what I'm going to do, and this is what you should do from now on, anytime you're given something like that, just plug it in, and then ask yourself, is this equal to 0? Because everything would be different if it is. If it is, we got some work to do. Okay? But if you just plug in your number, and the denominator is not 0, then you're done. So that's what all of those limit laws are about. That now we could do this. We could actually do some stuff. And all those laws are just to prove that, like, you don't need to go through each one of these steps. You might have a question that tells you to do that. I think I gave you one. Yes. Evaluate the limit and justify each step by indicating the appropriate limit laws. Just do something like this. Okay? And there's only one of those, and then we'll never do that again. From now on, or after you finish that problem, we're just going to say plug the number in and then see if the denominator is 0. Does that make sense?
Yes.
Why we're taking this huge jump now? Because the laws tell us we can. And those laws are justified by the rigorous definition of a limit. They're all derived from that. And so we can do this. We'll see that. And yeah. Okay, so here we go. This leads us to the direct substitution property. If f is a polynomial or rational function, and a rational function is just a ratio of 2 polynomials, okay? And A is in the domain of f. Okay, so like for instance, here's a rational function. 2x squared plus 9 over x minus 2. That's a rational function. What's not in the domain of that function?
2.
2, because if you plug in a 2, you divide by 0, so you can't define it, so it's not in the domain. But if it is in the domain, then the limit as x goes to a of f of x is simply f of a. In other words, just plug it in. Okay? That's all. That's what this means. Okay? Now, functions that have this property are called continuous. And not just polynomials or rational. This is just telling us that all polynomials and rational functions have this property. This is one. There are other kinds of functions which have this property. Like, for instance, e to the x has this property. Log x has this property. Square root of x squared plus 2 has this property. There's a lot of things that have this property. Those. What's that?
Do the trig function.
The trig functions all have this property, except for where they're, as long as, because some of them aren't defined at certain places, right? Like here, tangent is not defined at pi over 2, so it's not continuous at pi over 2. And you kind of see what I mean by continuous, right? And it's what you think it is. It's, can you draw it without picking up your pencil, right? Anything that you could draw on your page without picking up the pencil, without there being a hole, those are what we call continuous. We are going to get into that soon, but I just want you to know. So all functions that have this property are what we call the continuous functions. Okay? So, okay, without further ado. Questions? So in other words, this says just plug it in. If it's a polynomial or a rational, you could just plug it in, unless it blows up where you're going to plug it in. Because the domain of any polynomial is all real numbers. The domain of any rational function is all real numbers except for the ones that make the denominator blow up.
Yeah.
Right? So the only time we need to worry is where the denominator blows up. Oh, and lo and behold, here's an example of one where the denominator blows up. So we want to evaluate limit as x goes to 4 of, and this is number 14 from your book, x squared minus 4x all over x squared minus 3x minus 4. So you're given this and you're told evaluate. What's the first? Plug in a 4, right? So I'm going to do that. And I plug in, I get my 4 squared minus 4 times 4. And I get my 4 squared minus 3 times 4 minus 4. And I get, what's the bottom here? That's 16 minus 12.
Minus 4.
16 minus 12 minus 4.
Not good.
Uh-oh. Okay.
I'm gonna
Uh-oh.
have to do it.
And so...
Why can't you factor some?
Yeah, exactly. And so here's the thing. We can't just plug in a 4 because we get division by 0. In fact, I'm going to say the very first thing I should have done is forget about the top altogether. Because I just need to know. If that is not 0, then I could just plug along. The only way that this fails is if the denominator is 0, which it is. Now we got some work to do. Okay? So my only hope is to find a new function. So in other words, here we go. We have some function f. We're taking the limit of this function. This function is this right here. Okay? And if we were to graph it, it would look something like this. There.
You can't put it.
That's what this function would look like if I were to graph it. My hope, the only thing we could do, is find a function that looks exactly like this, but we just need it to be defined right here. This isn't defined there. Why? Well, can we factor that bottom?
It's like x plus
X
3x
plus-
minus. No, x plus
X plus 4 minus.
No,
X
x
plus 4
plus
times.
1, x minus 4.
Yeah.
I think so. First outer, inner, last, yes.
Yeah.
Outer minus 4, inner plus 1, minus 3,
three.
and then so yeah. Yeah. Okay? And actually what I would do, the way that whenever I do these, I start with the easier thing, and you'd see, you get that. And so that's like, if there's any hope, if there's any hope, remember we've done these before, right? Where it's like, simplify. And what I've suggested to do is do this, and then say, well, if there's any hope of simplification, either the bottom's going to be an x, going to factor into an x, or the bottom's going to factor into an x minus 4. So like that's going to be the first thing I write, and then try to figure that one out. However you want to do it, doesn't matter, right? But now we could see, you know what? Since those guys cancel out, there is a function. X over x plus 1.
You can plug it in 4.
It has the, and now we can't, so this function right here, if you were to graph it, it looks exactly the same as this function. The only difference is, it happens to be defined right there. And remember what we said before about limits, is like, we don't care whether or not this thing is defined at the place we're going to. All we care about is the behavior as we're going there. So if we could find a function g that has the exact same behavior, which this does, right? If you don't believe me, go home and graph these, right? They are exactly the same, except here at g, or here at 4, g is actually defined there. And that should make sense, because if I take g, if I take any function, right, like this, and I multiply it by 1, it hasn't changed anything, right? It's still exactly the same picture that I would draw, right?
Yes.
If I graph this, and then I graph this, we'd get exactly the same thing. And so it should be the case that if I do, I don't know, e to the x minus 1 over e to the x minus 1, I should get exactly the same thing, because that's just 1. No matter what value you plug in for x, that's always equal to 1.
Yeah.
Of course, we'd have a problem when x is equal to 0. Right? And so that, if I did that, now, technically, it's the exact same thing. I haven't changed it. It's still just multiplying this function g by 1, but now we have a technicality. If you plug in a 0, you get 1 minus 1, you get a 0 in the denominator. So technically, this function now, we would have to delete this guy.
You get a 1.
It's x plus 1 times 0.
E to the 0
Oh, which
is 1. 1 minus 1 would give me 0 here.
But
Right?
what about the x plus 1?
It's just
Like,
x
that
plus
gives
1
you a
times
1.
0.
That would give me 1.
Oh, times a 0. Yeah.
Yeah, times 0. yeah. Here, there you go, right?
Yep.
And so the way that I wrote this, it's not exactly the same as this now, right? It is different because now the graph has a hole. But aside from that hole, I haven't changed anything, have I? And so the limit as I go there, it's still going to the same place, right? Does everybody buy that?
Yeah.
And so that's what's going on here with these two functions. When I have my f, I have a hole right there. But I could rewrite f like this, and technically that hole is no longer there. And so with g, I could see, now I've constructed a new function that has the exact same values nearby 4. And we don't care about the actual, whether or not f is defined at 4, whether or not the hole is there. We just want to know what is the behavior as it goes there. So we can use this guy to find out. Does that make sense?
Yeah.
Does that make sense, Victor?
Yes.
Okay. So we're going to say the limit, now these functions are not equal, right? Like because of this stupid hole that you have to make sense of. But the limits are equal as we go to the place where the hole is. So I could say this is the same thing as the limit as x goes to 4 of this function. And now I don't have a problem. Can I plug in a 4?
Yes.
I can plug in a 4. And I could say that's the same thing as this, 4/5. And if you went through and did like you did, when we first did these and plugged in a bunch of values. You plug in 3.9, 3.999, 3.99999, and go from the other way, 4.01, 4.001, 4. Blah, 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 you would see that you're getting closer and closer to, what's that, 0.8 or something? Yeah, and so, okay, this is all consistent. So, that's it. That's the idea. If your denominator does blow up, or if your denominator does go to 0, our only hope is to rewrite this thing as a function that has the same values, but without the hole in the graph. In other words, can we remove the thing that makes the denominator equal to 0? And if we can, we could say, well, that's the same thing as this function. They're exactly the same except for the hole. And so we can do that because we don't care. We don't care about the hole when we're talking about a limit, right? We just care about the behavior as you're going towards it. Does that make sense?
Yeah.
Everybody get that? And so what we get is this principle here. And it's that if f of x equals g of x when x is not equal to a, which was the case with this function and our other one, they're equal wherever it's not equal to a, because this guy isn't defined at 4, right? But they're equal everywhere else. Then the limit as x goes to a of f of x is equal to the limit as x goes to a of g. Yeah. They're equal everywhere else. The only problem with one of them is at one single point. Okay? It's at that point, but that guy's just not defined. Well then, all we care about with limits, we don't care about the actual point itself, we care about the behavior going towards it. And so if they have the same behavior going towards a, then they're the same limit. Does that make sense? Yeah. Okay, great. All right. In this section, you could check out examples 3 and 4 for more on this. They give a slightly different presentation of what I just did. And I think it's kind of cooler than what I came up with. So you're welcome to delve into that if there's any questions you have on that. And that's in, it's on page 80 and 81. I'm going to do a good job explaining this further. So here we go. All right, number 22. The limit as h goes to 0. Should look familiar, of square root of 1 plus h minus 1 all over h. Okay, can we just plug it in?
No.
Well, we can see.
Well,
No.
No, because if we plug in a 0, we get division by 0. Ah. So our only hope is to find a new function which has the same values except at 0. Maybe, so in other words, we're looking for a function that does the same thing, but it's actually defined at 0. Here, my function of h, if I plug in 0, it's not defined, so there's a hole in the graph or whatever.
We could square the
Multiply.
top.
you can't square the top.
What can we do?
Multiply the top and bottom by
By what?
the square root of 1 plus h. Plus 1.
And that's the idea. Whenever you see a root in there, the idea is to rationalize it. Okay? And so, and then we don't know if that's going to do us any good, right? But remember, what I'm really doing is I'm multiplying this thing by 1, because I don't want to change the values overall. I just need to write 1 in a tricky way that's going to be to my benefit. So I'm going to write 1 as something over itself. And you already said it. We want the reciprocal of this thing, right? So we're going to take 1 plus h. Now, it's like, if you think about why did you do this 1,000 times in Algebra 2, right? This is why. This is why. If it weren't for this, like showing up, they never would have cared. But this is why you do it. So what does that give us on the top?
1
1 plus h.
plus
So
5.
first, outer, inner, last. First gives us 1 plus h.
Inner
Outer,
square,
inner is
they cancel
The
out.
outer, inner cancel out, and then
Minus 1.
minus 1. Okay, what about the bottom?
it's
H
h times
1 root 1 plus h.
I'm going to tell you something. Here's a trick. Here's a trick. My intuition is to go ahead and distribute this guy in. But oftentimes when you're dealing with something with roots in it, it's a lot easier to not do that. Because what's going to happen on the numerator? What's left over in the numerator after we...
Just H.
Just H.
We can cancel it.
Okay, cool. And oftentimes that's what happens. If I had taken that extra step and put him in, now I'd be looking at it going, what do I do? Well, maybe just hold off on the denominator. Or if you're doing it in the other way, hold off on the numerator and hopefully something's going to cancel, which it does.
Yeah, plus 1.
And now, here's the question. Okay, so here's a new function, or rather, thank you. I did this last night. I made the same mistake last night. So, here's the question. Is this function the same thing as that function?
No.
Okay, no. But is it equal to it everywhere that we care about?
Yes.
Right? Yeah. So, because all I've done is I multiplied it by 1. The only problem is, like, this one is not defined at 0. And this one may not, I don't care where it's not defined. But they have the same values everywhere except for 0. So, okay, so I could say then, now here's my question. Can I just plug in a 0?
Yes.
Yeah.
Yeah, I can. So I'm going to go ahead and say, okay, since these guys are equal, everywhere except 0, then this limit is the same thing as this limit, as h goes to 0 of this function. Right, this was my f, this is my g. And so I get 1 plus h minus, or plus 1. Now can I plug in a 0? Yep, I can. And I get 1, which is 1 over 2. Much easier than plugging in a bunch of crazy values and like you did at first, right? Yeah. And like I said, you'll never do that again. And not only because there's an easier way, but because remember, there were some times when we plugged in a bunch of values and it actually gave us the wrong thing. I did an example of that where like with sine, sine of like 5 pi x or something, or pi x, you always get 0, and so you assume, oh, it's 0. That can mislead you. Or rounding error can mislead you as well, right? So this is a much better way, and it happens to be much simpler. So that's the idea. If, in other words, we need to get rid, there's a problem here because that thing goes to 0. Can I rewrite this thing so that we don't have the problem? As soon as you get to a function that doesn't have that 0 problem, and you can plug in 0, go for it, and you're good to go. Questions? Okay, here's something, I wasn't even going to write this down. But I realized I needed to. Here's another thing we need to talk about. Limit as x goes to a of f of x equals some number. Okay. If and only if the limit as x goes to a to the left of f is equal to L, and can you guess what the rest?
The right.
And as it
Also
goes to the right, gives you the same thing. Yeah. Okay, like I said, I wasn't going to write this down. But it actually, as you'll see in the next example, this is actually important. But this is just saying that this limit exists only if and only if, the limits from both sides go to the same place, right? So you have, so like visually here, that was going to be stupid, but as you go to A, coming from this side, it goes to L, right? As you approach from this way, it goes to L. As you approach from this way, it also goes to L. As long as that's the case, then this is true. Yeah. Similarly, if I tell you, hey, it is true that this is the case, well, you could say, well, you must be going to L from both sides. You don't have some kind of crazy stuff like this going on, right? That's all that's saying. Who cares? And, like, now I don't know about you, but my head is in, like, polynomial space, because all the examples we've done is with polynomials. And you think, how could that possibly matter? Why would what you just wrote up on the board possibly matter? Who cares? obviously, we're never going to use that. Well, I assigned these. So, we want to figure out the limit as x goes to negative 6. And notice, that is not from the right or from the left. I'm saying we want to evaluate this guy right here. So what that thing I just wrote up on the board says is that if I'm going to evaluate, it had better work from both sides, right?
Yeah, that doesn't make sense.
Oh no! So real quick, the absolute value of x is equal to x if x is positive, right?
Yeah.
And it's equal to what if x is negative?
Negative x.
Negative x. So you take whatever's inside there, you make it negative. In other words, you multiply by -1 if x is less than 0. If what's inside of it is less than 0. So, let's see. X plus 6 is equal to x plus 6 if x is positive, and it's equal to what?
Negative x minus
X
6.
minus
Yeah, negative x minus 6 or negative x plus 6. Either way, right? Just make it negative, whatever it is, if x plus 6, right? Because it's whatever's inside, right?
Yeah.
Okay? Okay. Okay, so now here's the thing. Whenever you see absolute value, we have to think about both sides because this thing is no longer nice and smooth. If you think about if I were to graph
Oh, it all
y
goes
equals that, this thing looks like this, right?
Yeah.
And so we might have some problems depending on if you're going towards 0, you're doing this. If you're going towards 0 here, you're doing this. These are not the same thing. And so we have to think about this right here and say, okay. We're going to separate this out. We're going to approach from the left first. We're going to say, okay, the limit as x goes to negative 6 from the left of 2x plus 12 over x plus 6. And the question is, when we're approaching from the left, is this thing positive or negative?
It would be.
It's just
Wait, it would,
0. Blended.
it would always be positive.
So if x is on the left-hand side of 6,
It's negative.
that value is negative.
The absolute value of x plus 6.
No, it'd be positive. But
Wait.
since we take the absolute value, it'd be a positive number.
Wait a second. Take a number that's on the left-hand side of negative 6. So how about negative 7?
So it'd be negative.
Add that
1.
to 6. It's a negative
But then we
number.
take the absolute value.
And so we need to take the absolute value, so we need to make whatever that is negative,
Yeah.
right? So, goes to negative 6 from the left, 2x plus 12. Okay, so what I'm just saying is, when x is less than negative 6, then x plus 6 is less than 0, yeah?
Yes.
Right, so I'm doing this analytically now. I'm saying, okay. And therefore, the absolute value of the thing must be the negative of whatever it is. Right?
Yeah.
Since the value that's inside is a negative number, then we have to take the entire thing and make it negative. Yeah. Yuck. Okay. Is there any way we could simplify this stuff?
We can factor out a 2 from the top.
Factor out a 2 from the top. Okay, so now the limit as x goes to negative 6 from the left. 2 gets factored out. X plus what's left over on the top?
6. We can cancel.
And so there's a 6.
It's just
We can
negative.
cancel them. And so it's
Negative.
just the limit as x goes to negative 6 from the left of negative 2, which is a constant. And so it's equal to
Negative.
negative 2. Okay. Cool, so is the answer negative 2?
No, we need to check.
We better check the other side, okay? And so limit as x goes... Anytime you're dealing with limits and there's an absolute value in there, you had better check both sides. That is what that whole rigmarole was about, okay? So now, we're going towards -6, and we're on the right-hand side of it, and we're decreasing down towards it. So, since we're on the right-hand side,
That's always good.
-6 is less than x, and so 0 is less than x plus 6. So it's positive. What's in there is positive, and if it's positive, then what?
It's just x plus.
It's just x plus 6. Goes to -6 from the right. We have, I'm going to go ahead and do this. And now I can drop the absolute value bars because I know that what's in there is just what it is. We get +2.
They don't agree.
So they don't agree. Therefore, this
Does
limit
not exist.
does not exist. There you go. Okay? Because it doesn't agree from both sides. And it's if and only if. If they agree on both if the two limits agree, then that limit exists. And it's the same thing. If they don't agree, then it does not exist. Everybody got that? Finally, this is oh man, this is a stupid thing I gotta say. All right. Oh man, no, we're not gonna say it. We're just gonna blow through it because who cares? There's one more big important thing you need. I will just tell you the thing that we're blowing by is theorem 2 on page 83. It's obvious when you see it. Who cares? You'll see. You'll go, okay. I was gonna write it up, but now I'm not because we're running out of time. Finally, this one is very important. The squeeze theorem. Like if you squeeze a lemon, right? Squeeze. I don't know if I spelled it right.
Yeah.
I did. Nice. If f of x is less than or equal to g of x, and that's less than or equal to h of x, near a, except possibly at a, and that's one of those things, right? It might not be equal, right? Because that with limits, we don't care about the actual value at the actual number. And the limit as x goes to a of f of x is equal to the limit as x goes to a of h of x. And that's equal to some number. Okay, so the outermost ones have the same limit.
Then the inner one also.
Then the inner one also has the same limit. X goes to a of g of x is equal to that limit. Now, in pictures, what does this look like? We have, say, an H, and we have, say, an F, and we have a G. And here is my A right there. You'll notice that both F and H have the same limit at A. And since G is between them, near A, and it doesn't necessarily need to be like, F could have done this. Because we don't get, it's just near A that we care about, because we're talking about a limit. We're thinking about getting closer and closer and closer. That's what that near means, nearby. It's in a neighborhood of, okay? Then they have the same limit. Does that make sense?
Yeah. Yeah,
Okay.
yeah, that makes sense.
It does make sense. Good, okay. That's a squeeze theorem. There are squeeze theorems for other things besides limits that we will use later on this year. Squeeze theorem, very important. Why? Well, here's your final example right here. Find the limit as x goes to 0 of x squared cosine 1 over x.
So cannot plug in a 0.
We cannot plug in a 0. Oh man, it would be nice if we could just plug in a 0 because
Oh wait, but that's
you know, because you would be able to say like you know, this should be the same as this right here times the limit of the cosine. Because that's true,
Yeah.
but I can't plug in a 0. That limit doesn't exist. It bounces around forever. So what do? Well, we're going to use the squeeze theorem. And whenever you're doing stuff with trig, you probably want to start with the trig function and say cosine of anything is always between what and what?
One and negative one.
Yeah? Even if it's this?
Yeah.
Yeah, because like as you go towards 0, it may not be defined there, but again, we don't care about what it is at the actual place. As you go towards 0, it just bangs around even faster. So, okay, yeah, but it's always between there. It's just banging around between 1 and negative 1. Now we could say, well, you know what? I can multiply this entire thing across by x squared.
Oh yeah. Oh.
Interesting. And now I could say, wait a minute, we have that nifty, we have the squeeze theorem. Since this is true, I could take the limit as x goes to 0 of negative x squared. And that will be less than or equal to the limit as x goes to 0 of x squared cosine over x. And that'll be less than or equal to the limit as x goes to 0 of x squared. What's that limit?
0.
0.
And so is the other one. So it's also.
Oh, so.
Oh! Oh! And so, the only way that could be, and it's like, what that theorem tells us is that, yes, this means that that limit is equal to 0. Right? I like to write it like, this is, if I were deriving this, this is how I would write it. But you could just say, since this, and this, then the squeeze theorem tells us that this right here, this is sufficient for me. I mean, but really what this means then is that the limit as x goes to 0 of x squared cosine 1 over x is equal to 0.
Yeah.
Okay? And now, just real quick, what? So, what's going on here is we have our,
It's greater than 0, but also less.
so we have this function here, x squared, looks like this, and we have this function down here, negative x squared, looks like this,
Wait. Oh wait.
and therefore, this function right here, since it's always between it, what it does is something like this.
Yeah.
Oh.
And if you graph it, indeed, that is what you see. That's this guy right here. And so that's what's going on there. You've squeezed, in other words, if you could squeeze that function between two other functions, then you could guarantee that as this goes there, it actually does indeed go to 0. That is all. You guys have a good one.
Sound wave.
What's that?
Is that some type of like sound wave?
You know, like you could use this as an envelope. Remember we were talking about envelopes before?
Oh, okay.
This would, yeah, like that's what, you could definitely use that in like audio processing and stuff. But yeah, that's, anyway, so enjoy.